The absolute value function is a way to describe the magnitude or size of a number. Precisely, if x is any point along the number line, then the absolute value of x is defined to be the distance from x to the origin. For example, the absolute value of 2 is 2 because 2 is 2 units away from the origin. On the other hand, the absolute value of -3 is 3 because the point -3 is 3 units away from the origin. More generally, the absolute value function admits the piecewise definition, whereby its value at a point x is equal to x whenever x is positive and minus x whenever x is negative. This piecewise description allows us to graph the function in the plane. The region where x is positive is the region to the right of the y-axis, and there the function is equal to x, so we should graph the line y equals x. To the left of the y-axis, the function is equal to minus x, so we should graph the line y equals minus x. The resulting curve is a v-shape with a vertex at the origin. We can also notice that this curve enjoys an axis of symmetry about the y-axis. In other words, if we reflect the graph across the y-axis, then it remains the same. The absolute value function can be used in conjunction with other functions to produce new functions, such as this one, which we'd like to graph. To do this, let's first understand what this function does to an arbitrary point x. Directly applying the piecewise definition, this function is described by 2x minus 1 when 2x minus 1 is positive, and negative the quantity 2x minus 1 when 2x minus 1 is negative. By rearranging the inequality 2x minus 1 is greater than or equal to 0, we find that it's equivalent to the inequality x is greater than or equal to 1/2. This means that the region where 2x minus 1 is positive is just the region where x is greater than or equal to 1/2. In a similar way, we can find that the region where 2x minus 1 is negative is equivalent to the region where x is smaller than 1/2. What we've obtained then is an equivalent piecewise description of our function, as being equal to 2x minus 1 when x is larger than 1/2, and 1 minus 2x when x is smaller than 1/2. When drawing the graph then, we should draw two curves, one to the right of x equals 1/2, and one to the left. The curve to the right is the line y equals 2x minus 1, which has slope 2 and y-intercept minus 1, and the curve to the left is the line y equals 1 minus 2x, which has slope minus 2 and y-intercept 1. Another way of viewing this graph is that it is the piecewise linear curve that is obtained by reflecting the negative portion of the line y equals 2x minus 1 to the positive side of the y-axis. The methods just described apply to even more complicated situations. For example, this question has a polynomial inside of the absolute value. Thankfully, our technique from before applies, and using the piecewise definition, we find that we can write this absolute value of x squared minus 4 as being equal to x squared minus 4 when x squared minus 4 is positive, and 4 minus x squared when x squared minus 4 is negative. The difficulty in this case arises in understanding the regions where x squared minus 4 is positive or negative. Thankfully, we saw in a previous video that the roots of a polynomial divide the number line into pieces, on which the polynomial takes the same sign throughout. For this polynomial of x squared minus 4, the roots are 2 and minus 2. These points divide the number line into 3 pieces. On the middle piece, the polynomial is negative, and on the outer 2 pieces, the polynomial is positive. What this means is that the outer regions are those that apply to the upper piece of the piecewise definition, and the inner region is the one that applies to the lower piece of the piecewise definition. That is to say, if we were to graph this function, then on the inner region, that is, in the interval from x equals minus 2 to x equals 2, we should graph the function y equals 4 minus x squared, and everywhere else, we should graph the function y equals x squared minus 4. The resulting curve can also be thought of as the curve obtained from the graph of y equals x squared minus 4 by flipping all of the points with negative y component across the x-axis. The region we'd like is the region where the curve is above the line y equals 1. This horizontal line intersects the graph at 4 points, and the region along the x-axis where the graph is above this line consists of 3 intervals determined by these points. The endpoints of these intervals can be found from the points of intersection determined by the line y equals 1, and these points of intersection can be found by solving for x in the equalities 4 minus x squared equals 1 and x squared minus 4 equals 1. The solutions for x that you'd obtain are x equals plus or minus square root of 3 and x equals plus or minus square root of 5, respectively. Putting everything together, we find that the set in question is the union of 3 intervals: the interval from minus infinity to minus square root of 5, the interval from minus square root of 3 to square root of 3, and the interval from square root of 5 to infinity.